Okay, valence bond theory. We've been discussing the Lewis model and Vesper theory. And as I told you earlier, the Lewis model is an oversimplification. But it's relatively easy to understand, and it does work for a lot of things. There are more advanced bonding theories that we're going to look at. We're going to look at two of them, and they apply quantum mechanics to the idea of bonding in molecules. The modern quantitative approaches are very good at predicting bond length and bond strength, molecular geometries and dipole moments. They're quantitative. They involve a lot of math. We're not going to deal with them in their quantitative glory. We're going to look at two of them in a very qualitative manner. So the first one is valence bond theory. As we learned when we were talking about quantum mechanics, the electrons reside in quantum mechanical orbitals. These are localized on individual atoms. And these were those funny balloon-shaped things, right? I think it's best to think of those as standing waves that the electron is in. Remember, electrons behave as waves and as particles. So we've got these standing waves of different shapes because of the different nodes and things that they have. And there are four different shapes, types, S, P, D, and F. And these are atomic orbitals. These are orbitals on an atom. We can also combine some of those together and make hybridized orbitals. Okay, just like, they'll hybridize corn, a hybrid vehicle, right, runs on gasoline and electricity, either or. So hybrid is a combination. You can hybridize atomic orbitals. So the idea of valence bond theory is that orbitals overlapping is what forms the chemical bond. So when we have two atoms approaching each other, the electrons and the nucleus of one atom interact with the electrons in the nucleus of the other atom. There are repulsions between the nuclei, attractions between the electrons of one atom and the nucleus of the other atom. And valence bond theory looks at the energy changes resulting from those interactions. A chemical bond will form if the energy of the system is lowered by the interaction. If the interaction raises the energy of the system, you're not going to have a bond. It's only going to come together and form a bond if that lowers the energy. That makes it more stable. Question? No? Yes?
Making a bond is endothermic.
Bonds forming is exothermic.
And then
Breaking a bond is endothermic. So, again, with the endo-exo, we really have to get into our heads straight. What's going in? What's coming out? We're talking about the atoms forming the molecule as the system. So if they have formed a molecule and there's a bond there, we have to put energy into the molecule to break that bond. It's not going to spontaneously break. If it were to spontaneously break, there'd be no molecule in the first place, right? So what is harder to remember is that when bonds form, energy is released, okay? I think it's easiest to think of, okay, if I'm going to break that bond, I'm going to have to do something to it, right? I'm going to have to put energy in. Forming a bond is the opposite. So that means that forming the bond releases energy.
But wait, what if you're burning something? Isn't that breaking bonds? That's also releasing heat?
Yes, that's true. So when you burn something like natural gas, bonds are being broken, right? And we say, well, that's endothermic. How is this reaction releasing heat?
Because bonds are reformed to make CO2.
Because stronger bonds are being formed.
Oh,
Okay, so there's the energy needed to break the existing bonds,
because
but then there's
weaker if it's a bigger
yeah,
molecule.
but then there's the energy released when those stronger bonds form, and so that's why it's exothermic. Good question. So in this diagram, we're looking at two hydrogen atoms approaching each other. So on the x-axis, we have the distance between the two hydrogen atoms. On the y-axis, we have energy. So over here, when the atoms are far apart, the energy is close to zero. As they begin to approach each other, the energy is lowered because there's some interaction between them that's causing them to be more stable. As they get closer, the interaction becomes more and more stabilizing until we reach a maximum at this point. If we continue to push those two atoms closer together, now we get more repulsion from the two nuclei that are getting too close together. And so I kind of think of this like two people. So, maybe you've got a good buddy, right? You see him across the room, and you want to go over and talk to him, right? There's an attraction between you. But as you get closer and closer, you get to this perfect, like a sweet spot where you're talking and it's nice. But if you get pushed too close together, now it's like, hey, dude, you're in my personal space, right? And it's like, this is too close. So there's this perfect balance here where the energy is the lowest. And this energy here is the bond energy. So where the bond energy is maximum negative is the most stable place. And this distance here is the bond length. And what we see is those bond lengths are pretty consistent. You look at hydrogen molecules, two hydrogen atoms with a single bond. You look at a whole bunch of different hydrogen molecules, the bond lengths are all essentially the same, right? Because the atoms are the same. And so they get to this point where the stabilization is the maximum. Mm-hmm.
So is that something we're going to be calculating, or it's just...
No, we're not going to do any calculations in this. We're just, I think we're going to be counting to 6. Yeah. Yay! Woo! I know, it's still a little challenging, but I actually forgot what came after 5 yesterday, but I figured it out, so it was okay.
Use our fingers.
Yes, in fact, we will use our fingers.
So at the maximum, they have the most potential energy?
They have the lowest energy. Yeah. This is like a rock rolling down a hill. So here the potential energy is higher, and here it's the lowest. So the lowest potential energy, the lowest energy is the most stable. Yes?
Okay, so then when they're at the highest, that's when they're farthest apart from each other? Is that what you're saying?
Well, when they're far apart from each other, the energy is 0. There's really no interaction between them. Okay, so if getting these farther apart, increasing the distance, as we go over here, this line is approaching 0. The highest energy is when you try to push them too close together. Because as you get those positively charged nuclei closer and closer together, there's repulsion between them, right? And the reason that there's a dip here is because there's an attraction between the electrons of one atom and the nucleus of the other. There's also repulsion between the two nuclei. But this is where that balances out to be the lowest energy. Any other questions? So that interaction is usually negative. It's stabilizing. When the interacting orbitals have a total of 2 electrons, and those 2 electrons can spin pair, orient with opposing spin. So usually what happens is the electrons come from 2 half-filled orbitals. So one atom has a half-filled orbital, and the other atom has a half-filled orbital. Those 2 orbitals overlap, and the 2 electrons now spin pair. So one will be up and one will be down. If the atoms come together and both of those electrons have positive spin, one of them will flip so that they can be together. Okay, so it's like the orbitals in an individual atom. We saw that there was always a positive and a negative spin. You don't see 2 positive spin electrons in the same orbital. They're going to repel each other. Because it is kind of a mystery. How can 2 negative electrons be in the same orbital? But that spin is the factor that allows them to do that. Sometimes the 2 electrons come from a filled orbital on one atom overlapping with an empty orbital on another atom. This is not as usual, but it does happen. This is called a coordinate covalent bond. This is where one atom is providing both of the electrons, and the other atom is just providing an empty orbital. So when the two atoms approach, the orbitals overlap, and the electrons align themselves so that one's positive and one's negative. So summary, this is all about the valence electrons. The valence electrons in the molecule reside in quantum mechanical orbitals. And the bond results from the overlap of two half-filled orbitals, spin pairing of the two valence electrons. The geometry of those overlapping orbitals is what determines the shape of the molecule. So let's look at this. So here we have H2S. And what we're looking at here is just the valence electrons. And on the worksheet today, you only need to put the valence electrons in all those little orbital diagrams because the core electrons aren't doing anything. They're just sitting there. So here's the orbital diagram for sulfur's valence electrons. It's got 2 electrons in the 3s sublevel, and it's got 4 electrons in the 3p sublevel. Hydrogens each have 1 electron, and that's in the 1s. So this half-filled orbital of hydrogen can overlap with this half-filled p orbital of sulfur. And so here we're showing that. Here's 1 p orbital. Remember, the p orbital has 2 lobes, but that's just 1 orbital. So here's overlapping with 1, and here's the other hydrogen atom overlapping with the other half-filled p orbital. And then this other p orbital, there's 3 of them, this p orbital has a lone pair in it. That makes sense? So we've got those atomic orbitals, and they're just overlapping. So the actual bond angle that we measure here is 92 degrees. It's a little larger than what this is predicting. When we look at valence bond theory, that's what we're looking at, 90 degrees. When we look at Vesper theory predicts that the angle is less than 109.5. So let's just look at why that is real quick. So we draw the Lewis structure for H2S. And we look at the number of electron groups around the central atom. There's 4. How do 4 groups get away from each other? Tetrahedron. What's the angle on a tetrahedron? 109.5. Because there's 2 lone pairs here, we predict that the angle hydrogen, sulfur, hydrogen is going to be less than 109.5 because those lone pairs are going to be more repulsive, and they're going to squish the hydrogens together a little bit. So this is okay, right? Any questions?
For the figuration up there, why did you just put 3s and 3p for sulfur? Why didn't you put the beginning of the...
Because it's only the valence electrons that are involved in bonding. So we don't need to look at the 1s2, 2s2, 2p6. I mean, you can put those, but then it all gets very cluttered and you kind of lose track of what you're looking at. Just the valence electrons. Well, let's look at methane. That's another section. I've got to stop.